How does Chat GPT get on when answering some of the biggest open questions in particle physics? What's up, you scholars of enlightenment? Dr. Sam Gregson, particle physicist here again. I hope you've had a brilliant week and are really looking forward to the weekend. I need it because I desperately need to go get a haircut.
Who's scruffy looking?
Today, can Chat GPT handle some of the biggest open questions in particle physics? Excited discussion of Chat GPT is everywhere. Chat GPT is a natural language processing tool created by AI and research company OpenAI and allows the user to have human-like conversations and much more with a sophisticated chatbot. The language model can answer questions and assist you with tasks like composing emails, essays, and even code. I was interested to see how ChatGPT gets on when discussing some of the biggest open questions in fundamental physics. Today, we're going to introduce some of those massive open questions. We're going to let ChatGPT have a crack at answering them in a sensible manner. And then we're going to see if it gives brilliant original feedback and answers or fraudulent pie-in-the-sky gobbledygook. To help me do that, I'm going to be joined by three fantastic special guests. In the first part, I'm going to be joined by two brilliant theoretical physicists who are going to help me to introduce these massive open questions and put ChatGPT through its paces. First up, Professor Martin Bauer. Professor Bauer is a theoretical particle physicist who also works on quantum sensors and dark matter. He's an associate professor at Durham and a science board member for the Science and Technology Facilities Council, STFC. Second, Professor Patrick Meade. Professor Meade is a professor of physics at the C.N. Yang Institute for Theoretical Physics at Stony Brook University. He is also interested in current and future experiments that may elucidate the properties of the universe, including the possibilities for future lepton colliders and maybe a muon collider. To that end, Professor Meade was the lead author of the muon collider contribution to the US SNOMAS process. In the second half of today's discussion, I will talk with AI expert Ramsey Faragher, who's going to help me to dig into any intricacies of the output that ChatGPT gives us when trying to answer those massive open questions in physics. Ramsey is an expert in electronics, navigation, and sensor fusion. He's a Bi-Fellow of Queen's College, Cambridge, and the CTO, President, and Director of Focal Point Positioning Limited. He is a real-life James Bond Q, according to Top Gear magazine. If ChatGPT does well, he'll tell us why. If it does poorly, he'll also tell us why.
He chose poorly.
So I really couldn't hope for three better special guests to help me dig into the physics capabilities of ChatGPT. Let's see if we should be welcoming our physics AI overlords.
So, Professor, would you say it's time for everyone to panic? Yes, I would, Kent.
So first up, let's ask ChatGPT some massive open questions in particle physics, and let's assess how it gets on. Okay, so the way I see this working is I'll introduce a huge open question in fundamental particle physics. You two, as my theory experts, Martin and Patrick, you'll briefly outline the issue. A quick game is a good game. We'll ask ChatGPT for its thoughts on that huge open question. And then you can have a quick go at kind of assessing or marking how well ChatGPT has done and whether it's a good physics tutor for people out there. And then a little bit later on, or maybe afterwards, depending on the timing, my friend Ramsey, who's an expert in AI, is going to join and see how your assessments of ChatGPT went and maybe why they went that way. Does that sound good?
Yep, sounds great.
Right, good stuff. So I thought the first big open question we get into is the dark sector. So what is dark matter? So we hear this a lot. Patrick, I'll come to you first. What's a very brief outline of this question? What's the big deal here? Why are people always banging on about dark matter?
I mean, we are very confused. Gravity seems to tell us there's a lot of other stuff out there that we don't know what it is. Yeah, we're hoping, just like everything else in the universe, it has a particle-like explanation, but we don't know.
So there's huge amounts of matter out there. We know it's kind of an embarrassment, I guess, for us that we know about 5% of regular matter. This is your stars and planets and all these kind of things. And the other 95% seems to be made up of things we call dark because we don't really know much about them. So what does Chat GPT say about this? Well, it says, I asked it to tell me, what is dark matter made of? Keep it vaguely brief. It says, dark matter is a hypothetical type of matter that has not yet been directly observed, but is believed to make up approximately 85% of the matter in the universe, which sounds very much off. Its exact composition is unknown, but it does not interact with light, hence dark. Martin, any thoughts there? 85% seems like it's gone a bit wild.
Yeah, it doesn't sound too bad, to be honest, as a first go. Did you ask it to be brief, by the way?
I asked it to be brief because it went on for ages, but
Right.
the ages before was really just saying, oh, I don't want to be too specific and talking about all the uncertainties. But then it basically said exactly the same thing that it said here. So just to keep it a little bit brief, I asked it to do it in 50 words or less. And then I asked it what particles it's made up of. And it went into ideas of weakly interacting particles, WIMPs, potentially axions or sterile neutrinos. So, Martin, any thoughts about what it's come up with?
These three are all valid candidates, I would say. I think this is a reasonably good answer.
Okay, so do you want to give us a little bit of a rundown for people in the audience of maybe what these three are? Not going into too much detail, I guess, but why are we interested in these three things? WIMPs, sterile neutrinos, and what was the other one that it came up with? Axions. What are these things? Maybe if we go one at a time, Martin do one, and then Patrick jump on one.
So all our evidence for dark matter is gravitational. So all we really know is that it interacts gravitationally with the standard model. We have no observer that tells us otherwise so far. So beyond that, it's a question of what is allowed by the consistency of physical theories. And people have explored different options. One of those is the weakly interacting massive particle. They are basically guided by the coincidence that the mass scale of such a particle is around the electroweak scale if its interaction with the standard model is of the strength of the weak force. And why would it need this interaction? This is because if you assume that the abundance of dark matter in the universe is set by the same mechanism as the abundance of neutrinos or photons, then eventually they need to have decoupled early from the thermal bath with the standard model. So early on, the universe was very hot and dense. And then when the temperature dropped, particles that are too heavy to be produced at a certain temperature decoupled. And that it fits the bill if the coupling strength is the weak strength and the mass of these particles is roughly the weak scale. Now, direct detection experiments have excluded most of this parameter space, but not all. If you go to rather large masses, this is still allowed and is still actively being explored. So to say, the main target of direct detection experiments. They are not limited to this kind of dark matter, by the way. So they can detect everything that interacts with the standard model with an appropriate strength and a mass that is heavy enough to hit xenon atoms, say, and make it move. So, but roughly, this is what people mean when they say a WIMP or weakly interactive massive particle.
Do you want to, Patrick, do you want to have a stab at axions for us? Lots of strangely named particles jumping out in there in the description from Chat GPT.
Sure. I mean, this is kind of another class of ideas for what dark matter could be. It kind of takes us away from necessarily a particle-like solution for dark matter. And this is something that could have a very different mass scale, be a lot lighter, but still in terms of thinking of like a Bose-Einstein condensate or something else, that it could be acting like matter in our universe. I mean, it's one of the hot ideas for dark matter now because, like as Martin said, we haven't seen anything yet with these experiments, even though we're looking in many different places for WIMPs. And I mean, it's kind of an interesting segue where this is an idea that's been around that can think about dark matter, but it also is kind of motivated from a different direction where originally axions came about as trying to solve another problem in physics called the strong CP problem. And they're also kind of ubiquitous in string theory. So originally it's not like, hey, people said, let's come up with the idea of axions for dark matter, like WIMPs were just kind of this natural fit. But they can kind of fill in a different sort of parameter space for what things could be dark matter.
Interesting. Named after a washing detergent as well, I hear, because it clears up that strong CP problem. This was, I think is it in the US or Mexico? I can't remember where this detergent came from that that's named after. But I was told this. Martin, do you want to have a stab at sterile neutrinos for people out there? But just maybe give the people a vague idea of what those are.
Sterile neutrinos exist in theories that explain why neutrinos are massive. So the neutrino masses is one big hint that the standard model is not all there is. In the standard model, they are massless. And in order to make them massive, there are different possible ways to extend the theory. And one of them is to have sterile neutrinos. And when people say sterile neutrinos for dark matter, they talk a particular mass range where they provide a good fit. So this is usually lighter than a WIMP, but heavier than an axion. And that is another good motivation because we know we need an explanation for neutrino masses. And it's, it would be just an interesting option that this new particle that explains why neutrinos are massive could provide the missing matter in the universe.
It's always nice to have a hypothesis that hits 2 or 3 problems at the same time, right? This is this makes it more well motivated, perhaps. Excellent. So I'm going to keep a little bit of a running score because I've got 4 or 5 questions. How well do we think our AI companion did? If you were to ask this question, how would you mark its responses here? Maybe obviously it's hard at the start to get a scale, but on a scale of 1 to 10, let's say.
I mean, I'll let Martin go first.
Let Martin set the scale, and then you can go.
Exactly.
That's exactly right.
It's not too bad because you asked it for brief. So I would give it 8 out of 10. The 85%, I think, is like the mass, overall mass or something. I don't know what precise. It's not
I'm
very
not sure
precise.
what's decided that. I think it's found 85% left over and just sort of thrown that in. So maybe a little bit of a slip there. But I did ask it to be brief. So yeah, Patrick.
Yeah, I mean, I think it did pretty good in terms of grabbing kind of the main things. I think it's interesting that second question where it talks about like what particle is it made of, and it comes up with like axions, WIMPs, and stereo-neutrinos. It's kind of like axions are a big idea, WIMPs are a big idea, and then stereo-neutrino is like a very specific one. So it's kind of mix those together. So
it's you can tell that. I mean, these are things that I've heard of and don't necessarily know much about. So it's gone for the big headline things. You can tell that in its training data, it's gone and dredged up the main things that people will mention when they talk about these things, the main theoretical ideas. So, okay, we're not off to a bad start then. It did okay. The next big question that I gave it was related to scaling and the Higgs boson. So, why is the scale of particle physics, the Higgs mass, so small compared to the Planck scale? And I know you've talked about the idea of naturalness before, Patrick, when we talk about the Muon collider. Could you give us an idea of why is it a problem that the Higgs boson is so light and compared to the energy range that we might be able to reach or the universe might have been able to reach at some point?
Well, it's kind of weird where we have like all these different types of particles we've seen in the universe. And it turns out the types of particles that you can have is completely dictated by the symmetries of the universe we have. So that's why we hear about like spin-1/2 fermions, spin-1 gauge bosons. But a spin-0 particle had never been observed before until the Higgs. And it has weird properties in quantum field theory that describes everything that we know of, that it really shouldn't exist at a low scale. And that's why we apply quantum field theory to lots of other systems, whether it's condensed matter, nuclear physics, etc. And like you look up the table of like all the particles we know or like excitations of material, and you typically never see spin-0 particles. unless you've tuned the system in some way. So now we're confronted with this weird thing where they found it at the LHC. It's not easy to ever show up, and it wants to be kind of at the highest scales that you see when you calculate things in a quantum field theory. So it's a really bizarre problem. It's kind of like back in the days of when we had the Landau-Ginzburg model for superconductors, and it was just kind of like a simple phenomenological model. We found out hey, it wasn't actually just a boson or something actually inside of it, the Cooper pairs. So we're really mystified, and we have great ideas, but none have been found so far.
So is the idea, Martin, I guess, that kind of the universe and everything that we look at, the particles that we're made of, for example, and everything else, it seems to be at a very low energy scale compared to that Planck scale. Why is everything down here when we've got all of this sort of open space to use? Is that kind of the a grounding of the problem?
Well, you can put it that way. Of course, we also don't know whether there's more stuff at higher scales. We haven't tested them all. We have a theory that is consistent all the way to the Planck scale if you include neutrino masses. That makes it kind of a puzzle. But what Patrick said, what is more concerning in a way, or what is more unusual, is that if you have an elementary scalar like the Higgs boson, then its mass term is sensitive to arbitrarily high scales. So if there is some new physics up there, that means that somehow if you calculate at the low scale, in order to counter these effects in your theory, you have to know about these precise values. This is kind of counter the paradigm in effective field theory that we have learned. If this really exists, it's kind of against reductionism, if you will, like you would want to expect that the scales can be separated in a way, and you have a fully working model at a certain scale that doesn't care for what happens at a arbitrarily high scale. But the mass parameter of the Higgs boson in principle does do that if it is really elementary. On the other hand, we might just be completely wrong. It might be that the way we understand this, like the paradigm we have all learned this, and this has guided us so well constructing the whole standard model, fails here. And it just happens to be that what we call natural is not realized in nature.
So it looks very strange to us that it's down at these low scales when it's sensitive to potentially physics all the way up to the Planck scale. Very interesting. So I asked Chat GPT, why is the scale of particle physics, the Higgs mass, so much smaller than the Planck scale? And I asked it to be brief again because it waffled on for ages, but basically said the same thing. And it says the Higgs boson and other elementary particles interact through fundamental forces with much smaller masses than the Planck energy, which sounded a bit odd wording. The gravitational force is carried by a hypothetical particle called graviton, which is believed to have mass equal to 0. As a result, the gravitational force becomes significant only at very high energies, such as those found at the Planck scale. This is why the scale of particle physics, including the Higgs mass, is much smaller than the Planck scale. Seems to have got itself a little bit lost. Patrick, any thoughts on that one?
Yeah, it seemed to do a lot worse than the I mean, the words, the scales are in there, the Higgs is in there, but anything beyond that.
So I didn't force it to be bad with the 100 words. It basically said the same with a load of I don't know at the start, so I kind of cut that out. But yeah, it seems to have sort of, I'm not sure it's even dimensionally consistent, some of the things it's saying, but it has kind of the general ideas in there. It kind of has the idea, I guess, that the Planck scale is high and then gravity comes in at that kind of, or at least quantum gravity comes in at that point. But it seems to kind of run off into the weeds. It probably has a prong that says Planck scale and runs off over here, gravity, and then runs off over here, and then kind of tries to come back
found the words associated with the Planck scale, and then it also put it's because you asked it.
And then it's like, how do people usually put these together? Probably in these really bad exam question answers that I've just found. So here we go. Martin, any thoughts on this one? Not so good this time.
I mean, it kind of ducks the question, or it interprets it completely differently, right? You ask it, why is that the case?
And it's like, no, I've got another question. That this is what I used to do in exams for a long time. This is a real big problem. You know, where you read the question, but then you kind of answer the question that you want it to be because you know a lot more about that question. It's not like why, but it's maybe how. And I'm just going to write about how for a long time. But yeah, sorry, please continue, Martin.
Yeah, it's not. So there's some true things here, but you have to look for them. This gets in most like 2 or 3 out of 10 if you need to get it. Give it some grades.
2 or 3. So this one's no good. Patrick, we're going 2 or 3. You happy with that?
Yeah, I think that's a good rating for this one. It's definitely failing on this question.
Good. Is there any thoughts of how we're going to fix this? Because I guess the great hope for this was Susie, right? That this was going to sort of stabilize things, and we were going to find all these new particles at the LHC, and this was all going to be happy days again. But obviously we haven't found this at the LHC. Is there any way to counter this, Martin, that we think at the moment? What's the best theory at the moment, or the leading theory?
I don't think there is a leading theory. That's part of the problem. I don't think any of the theories, we have no experimental data that prefers one explanation over another, over no explanation. So we don't really know at the moment. Supersymmetry has been proclaimed dead several times. And obviously there's like the theory was never supposed to be supersymmetric as actually realized in nature, but there has to be a gap in the masses between the observed particles and their superpartners. In terms of string theory or gravitational quantized gravitational theories, if you want this realized, then supersymmetry need not be existing with a very small gap. In terms of that, the superpartners could be much heavier. But if you want to address naturalness, by now already we know that they must be so heavy that this is extremely stretched. So I don't think there is any other theory or any other system in nature, maybe just so, but not one I'm aware of, where the gap in terms of tuning that you would need for the mass parameter would need to be stronger than it is for the standard model in the Higgs mass.
I remember one of my lecturers in Cambridge, Andy Parker, described Susie as the theorist's pension plan. I don't know how you feel about that terminology. Seems like they just tweak some parameters, come back, and it never dies. But it seems to have got really squeezed now, Patrick, right?
Yeah, I mean, I think like there's also the famous Glashow comment, like supersymmetry is great. We've already found half the particles. But at the same time, I mean, I think it depends kind of on what direction you take it from. Like Martin said, there's not a particular leading theory to explain naturalness because we haven't found any signs of it right now. I think the reason why supersymmetry is particularly compelling, though, is not that it has lots of extra particles. We also have this weird thing where like every kind of layer in nature, when we go to shorter and shorter distances and find things, it always kind of comes with new principles too. And those principles become more and more restrictive kind of at every layer in terms of like when you go from classical physics to quantum physics, to quantum field theory, like the possibilities become smaller, and there's a fundamental principle of what's going on there. And supersymmetry, I mean, like from the phenomenological point of view, lots of particles, it seems crazy, but it is kind of interesting that there aren't that many different things you can do to space-time that come up with new symmetry. So that's why I think it's still such a compelling idea theoretically. And the real question is kind of how do you reconcile this principle of naturalness with this big idea? And like Martin said, it doesn't have to be very light. And in fact, when they found the Higgs at 125 GeV, it actually prefers supersymmetric particles to be quite heavier to explain that mass. So we're still kind of in the kind of unsure zone. And it really will require us probing nature further to figure this out.
And that's why we need a Muon collider.
Exactly.
I know. Good. I always like this one because it's got the the Higgs Xenos and the strangely named particles that sound like Brazilian footballers. So I remember always enjoying this one when I was learning about it. Good. Right. So not so good on naturalness, 2 or 3 out of 10. Better on the previous question. So the third question I had is where is all the antimatter? So I can give a little bit of rundown for this, I guess, with as an old LHCb guy. So all of the particles in our models we expect to have an antiparticle. So electron has a antiparticle, a positron, and we believe that in the very early universe, equal amounts of this matter and antimatter were created. But nowadays, we only see what we label matter. So positive protons, negative electrons. And these are just labels that we've put on things. And the question is, where has all of the what we call antimatter gone? And one of the ideas is this idea of CP violation, where there's a slight difference between the behavior of matter and antimatter. So you start off with these equal amounts in the early universe. One of them decays away slightly faster, the antimatter perhaps. You get a little bit of imbalance. They come together. They annihilate one another. You have a little bit of matter left over and lots of light. And that's kind of what our universe is like nowadays. Lots and lots of light flying around and little bits of matter. So I asked Chat GPT, are we happy with my old school LHB explanation there? I'm a little bit rusty.
Yeah,
we're happy.
Works.
CP Violet, good, excellent. So I asked it, where has all of the antimatter gone? And it came up with this answer. So this is what happens if you don't make it be brief, right? It goes on and explains to you what antimatter is, what we talked about. While the universe is thought to have been created with equal amounts of matter and antimatter today, only a small fraction of the universe appears to be made up of antimatter. Scientists are still trying to understand why this is the case, and several theories have been proposed. One possibility is that there are regions of the universe where antimatter exists in large quantities, but they have not yet been detected. Another theory is that there may be subtle differences in behavior of matter and antimatter that allowed more matter than antimatter to survive after the Big Bang. So there's your CP violation. Currently, researchers are using particle accelerators and other experimental methods to study the properties of matter and antimatter. So for me, I think this is quite a good answer, except this bit with the huge areas of matter and antimatter. If you had those areas, if they existed, I would have expected them to have shown up in the CMB already, because they'd be very, very violent areas, right, between areas of matter and antimatter. But I'm sure some cosmologists will tell me they're behind horizons, or we can't see them, or they're in another universe, a parallel universe. How do we feel about the answer that Chat GPT's come up with for this one? Martin, I'll go to you. So when I have more than one person, I have to remember to go to individual. Martin, we'll kick off with you.
I think I agree with what you said. I don't think there's any serious theory that I'm aware of, at least, that can separate the matter from the antimatter through any kind of mechanism. And even if it were the case, like you say, there would need to be some kind of area where the two bubbles touch, and that would be an area where we would have a lot of annihilation and a lot of light that you could detect from there. So I don't think this is in any way a leading or serious theory that can explain why we see mostly matter. And if you put it behind the horizon or in another universe, you might as well just not call it a theory, right? Exactly. So at that point, unless you can present such a mechanism that I haven't seen. So I think you're right. I wonder also why it's not talking about CP violation at all. Right? That's a bit surprising.
It kind of puts it here, but never mentions CP violation.
A little different.
Yeah, it sort of puts it in layman's terms, I guess, with this
right.
allowed more matter than antimatter to survive, which is sort of the hand wavy way of, or a lay explanation of it without giving you any sort of details. So it kind of does, but it kind of puts it on a par with this other one, which isn't really. So it's probably, I would give it another 7, 8 maybe, but it's probably put them on a par when they probably shouldn't be. Patrick, any thoughts?
Yeah, I mean, I think it's interesting how, similar to the first question on dark matter, where it kind of like tries to pull out specific ideas, where it like throws out this kind of voids and putting antimatter somewhere else on like the same page, just like it kind of like the big ideas of WIMPs, and then it took a really specific one of sterile neutrinos. So yeah, I mean, I'd probably say 6 or 7 on this. I mean, it'd be interesting. I wonder if like the training set with all the literature on dark matter is like, maybe it's like so much larger than the matter antimatter asymmetry that like it seemed to pick the better ideas for that one, whereas this one kind of picked not a very favorite idea, because you'd see all this light from the interaction of matter antimatter. So yeah, it's curious, like how much.
Imagine the CP violation training set is too like voluminous.
It's smaller than dark matter.
Yeah, the smaller than the dark matter training set. I think you're probably onto something there. Is I should ask the theorists at this stage. So the level of CP violation which is allowed in the standard model is not big enough to explain the universe we see today. Obviously, there's various mechanisms proposed for CP violation beyond the standard model. Is there Are there any leading theories at the moment for where the CP violation could be hiding? I guess in the neutrino sector, potentially there's ongoing efforts there. Martin, any ideas?
Yeah, so you need complex interactions to have a CP violating phase in your theories. So you could have that in the neutrino sector. The standard model is not alone for the standard model itself to explain it. But there are also theories where, for example, you have additional dark matter particles that interact with B mesons that then inherit to this mechanism the CP violation, and they could generate what we have observed. So you need to extend the standard model in some way. And obviously, it's dark matter and neutrino masses are two ways where we think it absolutely needs to be extended. So these are, if you want to talk about leading theories, these are at least well motivated. That maybe again there's one puzzle, and maybe a theory that can solve it can also solve another puzzle.
That's always a good thing. Like we said, I remember when I was going through Cambridge, basically every new theory had a lighter stable particle, and they were like, okay, that's a dark matter candidate. So they were always kind of hooking it onto dark matter as well as a solution for that. So I guess here, not too bad again, and probably, as Patrick says, because the training set for antimatter dark matter is probably bigger than the training set for dark matter is probably a bit bigger than antimatter, so it's probably a little bit better for the dark matter here than the antimatter, but not too bad again.
You also let it talk more. So
that's true. That's true.
It only started throwing these exotic theories around once it's in the third paragraph.
that is fair. So what it tended to do when I let it waffle is it tells me all the things it doesn't know to start with, and I'm like, okay, get to the point. Come on. And then you're right. When you give it a little bit more leeway to kind of go off, once it's got its disclaimers out of the way, which I guess the coders have put in there to make sure it doesn't say anything stupid, then it will say, okay, with all that said, I'll now open up a little bit. So yeah, I think that's probably.
I mean, one other just comment based on like the question you made, like in the dark matter case, like you specifically said, like what is dark matter made of? Whereas this one, it says, where is all the antimatter in the universe? Whereas like I wonder if you said like, why is there more matter than antimatter? Yeah. Like kind of seeding it more directly onto that question rather than where the antimatter go. That's why maybe gave us kind of the more messy, it's hiding behind something.
So this is also a really, really important point, and I'm going to discuss this in the second section when we finish with Ramsey. What he calls, and I guess is more widely called, prompt engineering, right? Because depending on what you ask it, you get a very, very different answer, right? And I tried to get sensible answers, and I tried various variations, but a small change, as you've correctly said, can give you a wildly different answer because I guess it seeds it differently. It has different links. It has different words that it jumps off and forks with. So yes, this is very important to get good prompt engineering. So when you're asking a question, it pays to be very specific.
Which is true for humans too, right? If you have polls and you slightly change the question, your result can vastly vary.
And even when they do like the converse, if you ask a particular question, then you say, or do you not think that, you'll see a huge difference between the response. So yeah, it's very, very important is your prompt engineering, which we'll discuss a little bit more with Ramsey afterwards. Okay, now Martin, you mentioned this as we were going along. The fourth question of 5 that I've got, which is, where do neutrinos get their mass from, and why is it so small? So, Martin, do you want to briefly outline the issue here, and we'll get into this one?
So it's an open question. We don't have a leading theory on that, but there's a limited number of possibilities. At least if you constrain yourself to minimal extensions of the standard model, of course, you can always have more than that. But if you only add what is absolutely necessary to make the neutrinos massive, there's a bunch of possibilities. Mostly people distinguish between direct neutrinos and Meade neutrinos. And Meade neutrinos are what you get when the neutrinos are their own antiparticle. And you can have that, for example, when the right-hand neutrinos, the neutrino partners, are extremely heavy. So then you generate an operator that gives mass to the neutrinos, where the neutrinos are their own antiparticles. And the opposite of that would be when the right-handed neutrinos are exactly the same mass as the left-handed neutrinos. That's what people call Dirac neutrinos. And then you have the stellar neutrino label, which is usually assigned to anything in between, to a right-handed neutrino that has a mass parameter that is distinct from just the Dirac mass, but it is not necessarily so heavy that you can completely integrate it out and take it away from the theory. Why they are so light is not really explained in any of these theories in a fundamental sense. Like you could argue that because they are not charged, that allows them to be Majorana particle, and therefore this has the inbuilt possibility of having the right-handed partners being so heavy, and as a consequence, the left-handed partners being so light. So that is, in terms of an explanation, as close as you can get. And then, of course, all these theories have their own inbuilt mechanism that explains it. But fundamentally, we don't really know why they are lighter than the other particles that we see.
So let's see what Chat GPT had to say. We don't know, but maybe Chat GPT does. So it says, in the standard model of particle physics, neutrinos are initially assumed to be massless particles, so they don't get their mass from the Higgs like we're used to. However, experiments have shown that neutrinos do have mass, so this is neutrino oscillations, and it's small but not zero. One possible explanation for this mechanism is known as the mechanism known as the seesaw mechanism. This mechanism involves introducing very large particles, which you mentioned, known as right-handed neutrinos, which do not interact with other particles in the standard model except through gravity. The interaction between the right-handed neutrinos and the left-handed neutrinos, which are the ones that we observe in experiments, can result in a tiny mass for the left-handed neutrinos, even though the right-handed neutrinos themselves have very large masses. Patrick, any thoughts so far?
Well, I mean, like, it has the words at some level, but if you look at the statement where it says, like, I think it says the right-hand neutrinos, which do not interact with the other particles in the standard model except their gravity. And then literally the next sentence, the interaction between the right-hand neutrinos and the left-hand neutrinos, which are in the standard model. So, I mean, like, it has the buzzwords that I think you grab fast, but it's like that logical consistency is not enforced in any way because it's just finding the words rather than thinking through this.
So I'm trying to think my notes. There wouldn't be an interaction if it was like completely massless, right? Because it would be totally left-handed. But there is a slight interaction. It's just not very big. So
I mean, whatever mass mechanism it is, it has to actually interact with electroweak symmetry breaking. So it has to talk to the Higgs or has to talk to a new Higgs, regardless of whether it's right-hand neutrinos or anything else. So there's definitely other interactions there, even if it's a right-hand neutrino. But at least kind of the buzzword like seesaw mechanism and right-hand neutrino, the big thing is there. So
what I get from this, and it's being we saw it in the previous one as well, is I think it's very good at doing what some people might call kind of blagging or bullshitting. Like, it knows the key words. If I'm talking to someone who's not too experts like yourself, I'll probably get away with it. If I'm talking to, a layperson, talk about seesaw mechanisms there's kind of interactions going on. People will be like, oh yeah, he kind of sounds like he knows what he's talking about. But if you probably got up in front of a class of theorists and started saying this, people would probably raise some eyebrows. Martin, any thoughts?
Yeah, it's clear what it wants to say, but Patrick is, of course, completely right. I wonder does it ever cross-check sentences, or does it just go word by word? Do you know that?
I think it go. How do you mean by cross-check? I know it definitely goes word by word, but how do you mean by cross-check? And I'll check this with Ramsey in the second part as well.
I think it wouldn't be too difficult. So if you had two sentences, you can make it even clearer. You can say, one sentence, there is no interaction. The next sentence could be, the only interaction is this.
You mean, does it talk to itself based on what it's already said?
Yeah, obviously it doesn't, right? But it would be interesting to see. It doesn't sound like this would be impossible to engineer, that at least the obvious contradictions be filtered out.
Yeah, it doesn't seem like it does that, does it? And I've seen it do even worse things than this, where it just says something is A and then says something is B in the next sentence. So this does seem to be a problem. I think if you regenerate it and tell it that that's a problem, it can potentially incorporate that idea and tease that out. But I think you're right. It doesn't think too carefully about what it's already said, giving its next answer. It just keeps using its training data from the past. So that's a very good point. And then it keeps going on about and mentions, it gets in the sterile neutrinos in inverted commas and the Majorana in inverted commas as well, to kind of round out the ideas that you said. So what are we thinking here? 3s and 4s again? Not so good.
I don't know. Maybe I'm a generous grader. I give it in like the 5s sort of category. I mean,
This is a kind of marker I hope I get on my exams, right? I'm like, keyword there, tick, that's kind of lower level marker.
I mean, I think like you mentioned it earlier on one of the questions. I mean, it really does kind of a smack of a student that like gets the exam, they didn't study, but they're like trying to put as many things together to.
I have a student. He's a really good student, but as soon as he sees a question, like a word will be in there, and it's just like, I don't know, kinetic energy, and he's just like, oh my god, half mv squared, things moving, and he just throws so much stuff, and in there are the 3 marks that are in the question, but it's like half a page long, like talking about like rockets and cars and stuff that was never asked about. So I think this is probably quite similar to what's going on. Martin, any closing, grading on that, closing remarks, and we'll move on to the next one.
I think I agree with Patrick. It really looks like let me fill the page and get some marks for that.
This is when I remember doing exams in Cambridge. If I turned over and went like, no, that question's too hard, you went back to the essay questions, and you were like, okay, I think I can probably squeeze out like 3/4 of the marks in that question just by writing like 4 pages of stuff. So yeah, I think that's exactly what's happened here. Good. Right. What have we got for the? So we've done 4 questions. I've got one more serious question. So I asked it, is it possible, or how would it be possible to combine general relativity and quantum mechanics? So this is a huge question. Patrick, do you want to outline briefly for the people watching what the big problem here is? Why is there a big stink about general relativity and quantum field theory?
I mean, it kind of at the most basic level, it's a matter of trying to understand whether we can have predictive theories in some sense. Like, we can still talk about quantum mechanics and general relativity at very low scales. I mean, you can ask, for instance, like, what are the quantum corrections from gravity to Newtonian potentials or things like this? As long as I talk about scales much lower than this infamous Planck scale that we talked about earlier, you can talk about both things at the same time. The problem arises when you talk about quantum mechanics and gravity at these very short distance scales. And the theory that we have of just trying to put quantum field theory with GR together, it just gives you kind of nonsense answers. There's no prediction left anymore.
So when people are talking about gravity, they might be used to this kind of GMM over R squared. But if you bring those very, very close together, the R's are going to 0. So what the hell's going on there? It can't quite be right at some scale. Something goes wrong. Our understanding is not quite there. There must be some sort of quantum scale thing going on that we don't understand.
And we have that kind of issue, like just in like electromagnetism, you still have like a potential that goes like 1 over R.
Yeah.
The difference is in the context of electromagnetism, you know what happens in that limit. Whereas you take our best theories of quantum field theory and general relativity, you do that with gravity, and you don't get sensible answers that come out of it.
So with quantum electrodynamics, with electricity, we can start talking about photons, individual photons being flitting back and forth between charges. But for masses, we don't seem to have that, do we, Martin? We don't have an exchange particle for gravity like we have the photon for electromagnetism, or we have the gluon for the strong force. That's a big problem, isn't it?
Yeah, it's not what you get in general relativity if you go to high energy. So we understand, well, if you have a quantum field theory and you go to higher and higher energies, you resolve things in shorter and smaller scales. But that's not what general relativity tells you. General relativity tells you if you go to very high energies, or if you bring a lot of charge, a lot of mass at one point, you get a black hole. And if you put more in, the black hole grows. So it's not true that you resolve smaller and smaller energy scales. Quite the opposite. You have a completely different behavior at the so-called UV for general relativity than you have for quantum field theory. So not only do they not go well together, but I think we're pretty sure that the quantum field theory, apart from asymptotic safety ideas, there's no good theory that might explain why how gravity could ever be a quantum field theory in the first place.
So I asked Chat GPT how we could put these things together. Or I said, is gravity fundamentally quantum in nature? So the question of whether gravity is fundamentally quantum in nature is an area of active research and debate in theoretical physics. Currently, the most successful theory of gravity is general relativity, which describes gravity as the curvature of space-time caused by the presence of mass and energy. General relativity is a classical theory, meaning that it does not incorporate the principles of quantum mechanics, which describe the behavior of matter and energy on very small scales. Martin, this sounds like the script I sent you the other week. It's like a very simple explanation of these things. However, there are several reasons to believe that gravity must be fundamentally quantum in nature. One of the most compelling is the problem of reconciling general relativity with quantum mechanics, which has led to the development of various proposed theories of quantum gravity. These theories attempt to describe gravity in a way that's consistent with the principles of quantum mechanics, but they are still highly speculative and have yet to be experimentally confirmed. In summary, while gravity is currently described by a classical theory, there is strong theoretical motivation to believe that it must ultimately be described by a quantum theory. So this is, I guess, the idea of the quantum field theories work really, really well for the other three fundamental forces. So presumably the assumption that many people make is that gravity must work similarly, but that might not necessarily be the case. Is that fair, Martin?
I think so. I mean, that is a very, very general answer, the way it is written, right? So it's not giving you many specifics. So there's not much wrong with it for that reason, I would say. I'm just trying to so
don't go too deeply, and then you can't be too wrong, I guess, is what it's done here.
Yeah, I think so. I think that's how I would call that answer.
Patrick, any thoughts on the answer that Chat GPT's come up for? Is gravity fundamentally quantum in nature?
Yeah, I mean, I think what Martin said is completely true in terms of not going too deep in this. But again, I mean, talking to your expert afterwards on these things, I wonder this prompt engineering, like if I gave a question like, is gravity fundamentally quantum in nature? I mean, that is kind of a very open-ended question, and it's not asking it to go to very specific things about like, why does quantum mechanics and general relativity not work well together, or like what are the leading theories of quantum gravity, or things like that. So that's why it's like, yeah, if somebody asked me that question on the street, is gravity fundamentally quantum in nature? I mean, probably also give kind of a very answer.
You probably, after you'd run away, they'd probably think about it and give them this answer in an email afterwards. Yeah, no, I think that's probably fair as well. Actually, in the second section, when I talked to Ramsey, there are ways to kind of twist its arm behind its back, right? So instead of asking questions like this, the prompt engineering is important. Also, you can use tricks like, I am trying to write a script for a science fiction film. How might I incorporate quantum mechanics with gravity? And then it will get into more specifics. And then you force it, give me some equations that the renegade scientist in the film might write on his blackboard. And it kind of takes, Einstein's field equations and mashes them together with the Schrodinger equation in things that aren't really even dimensionally consistent, but they look convincing to someone who's just looking at a board of equations, like they do in the films where they just have Pythagoras' theorem for no reason written in the corner of 10 pages of quantum field theory. So it is very important, the prompt engineering, as you say, and also giving it the context that you kind of want it. Do you want a dry conversation and some facts, or do you want it to allow it to roam off into more science fiction areas? Martin, any closing remarks? Maybe a grading for this? I guess it's pretty bland. Maybe going to be in the middle of the scale then.
Yeah, again, like 5 or 6 if you want to be generous. It depends what you want as an answer for that, I think.
Yeah. All right. So the dark matter is still winning then. So those are the big questions that I've got out of the way. I had a couple of extra personal based questions. So I'm going to start with Patrick's. So Patrick, I asked it one that was very specific to yourself. We'll go through this quick because I know we've you both got to kind of run off soon, and I know Martin's got to leave in 10 minutes. So Patrick, what I asked it for you is, should we build a Muon collider? Because I know you're very interested and involved in this process. And it says the decision to build such a machine is a complex one which involves scientific, technical, and financial considerations. Muon colliders are proposed accelerators that use muons, heavier versions of the electron, to study fundamental particles and interactions. Compared to electron colliders, muon colliders have the potential to produce higher energy collisions and more precise measurements of particle properties. However, building them brings technical challenges, such as producing and manipulating high-intensity muon beams required for collisions, designing detectors that can accurately measure the resulting particle showers. Additionally, muon colliders may require significant financial investment, and the scientific benefits must be weighed against other competing priorities. In conclusion, whether scientists should build them depends on a careful assessment of scientific, technical, and financial considerations. Seems fair enough. Maybe a little bit, you might have a comment on the price, which...
I mean, I think that somehow Chat GPT is secretly many government.
It's found your document. Just copied it out.
I mean, that last paragraph, I think is. I mean, as Martin probably can attest to, anybody that's been on a funding panel or anything, the very politically correct answer of.
Who drew this up? A lot of these aren't proper sentences.
It's legalese, all right? Keep your beak out.
Cut
How
and
we should
paste.
investigate things.
It's just, I'm going to give an opinion, but then I'm just going to say, well, it needs a lot more discussion between all stakeholders.
Exactly.
Is that a fair answer? Do you think? Martin? Do you think that's a fair answer?
Yeah, it's like the previous one. It's not really answering the question at all, right?
It's very non-committal, is Chat GPT. Very non-committal.
Yeah.
It gets in the key things again, though, like we say. So it's got the higher energies, the problems with the muon beam, so the muon cooling, which we've got some examples at MICE in the UK, and then dealing with the large amounts of particle showers from the decaying muons. So it hits quite a lot of the key ideas in quite a short period of time. So I guess your technical documents, Patrick, are part of the training set for Chat GPT. It's been having a look.
How you brought up also, I think, with the antimatter question, where the way it phrases certain things, if you're an expert, you can kind of read the phrasing and say, oh, it's obviously talking about all that. Like it gave like just muon beams and like, because you and I have chatted about this, like we know what the issues are. But at the same time, you could kind of like say those words about anything, or like didn't explicitly say like CP violation. It said the subtle differences between matter and antimatter.
It's not necessarily a good answer if you can just swap in like ice cream. Like ice cream is wonderful, but whether you should eat it is a question that you should discuss with your dietitian, your doctor. Yeah, it's kind of leaves it very bland and non-committal. It doesn't tell you to actually kind of action anything or do anything or write anything down. Yeah, keeps it quite vague. Martin, to finish off, I gave it one to play with for yourself as well. So I let it loose on one of your jokes. So Martin put out a really good joke, which I really enjoyed the other day. He said, the shortest history of fundamental physics is Newton changing sums to integrals and Planck changing integrals back to sums. So I asked ChatGPT, is it fair to categorize the history of fundamental physics in those terms? And it wasn't particularly happy with you, Martin, which we might flag up that ChatGPT is a humorless pedant, right? It understands what you were trying to say, but it has no irony or humor. And maybe, again, it comes back to prompt engineering. You have to tell it, is it a good joke to put it in these terms? Because if you don't tell it that, it kind of destroys people when they're just making a joke. So it says, while it's true that the development of fundamental physics has involved the use of both sums and integrals, it would be unfair and overly simplistic to reduce the entire history of fundamental physics to two mathematical operations. Newton did develop calculus and use integrals, and this was a step forward, enabling behavior of particles in motion to be explained. However, the history of fundamental physics involves much more than just the use of integrals. So it kind of goes in on you, Martin, a little bit. Obviously, I didn't expect you to give the experimentalists any sort of credit. That was baked in, but it's kind of savaged you here. What? Any thoughts?
It is pretty brutal, I must say. I think, unfortunately, it's also right, of course. But
it's not. It's not in context. It's not right. It is.
You should.
The words that it says are correct, like factually, but the fact that it's a joke is not taken into account at all, right?
Yeah, you would probably have to tell him that. But I think, honestly, to be fair, you should ask it to provide a better history of physics in 20 characters or something, and see what it comes up with.
So yeah, that's probably a good idea. I'll add that in. It'll appear on the screen. But yes, the main thing that I took away from this is that it can't do context, it can't do irony, it can't do jokes unless you specifically tell it. And I guess that comes back to the prompt engineering again. So, gentlemen, which one are we going with as the best answer, do we think? And how would we say Chat GPT has got on as a kind of tutor, as a kind of encyclopedia for answers to some of the biggest open questions in physics? I'll go to Patrick first.
I definitely say it did best at the dark matter answer. And I mean, I definitely think it probably shouldn't be used too much as a tutor unless the person has very specific questions they want answered. I'd be curious, like, I mean, this has been a fun exercise on kind of the concepts.
Yeah.
But like in terms of this logical consistency we brought up a couple times, like, does it do better if you ask it more like mathematical sorts of questions? Yeah. I mean, you mentioned like give some equations for a movie, it just gave you gobbledygook. But I've also seen like on social media, like it talks about like it can generate code snippets and things like that are functional pretty well. So I'd be curious, like at the level of logical consistency with words, it doesn't seem to work too well, like sentence to sentence.
Yeah.
But if you kind of had a more strict environment of like math things showing up, whether it would do better or not.
So you're absolutely right. And that all of these, the intention was to take all of your comments as experts and then give them to the AI expert and say, look, are they correct? Is this why it's falling down? Is this why it's doing well here? Is this why it's doing badly here? That's what we're going to follow up with in the second section. And that's exactly right. And that's what we should do. Martin, your thoughts on how well it's done and how maybe we should use this thing?
Yeah, I think I would be very careful with using it as a tutor, even if it gets more advanced, because it doesn't really, there's no, as far as I understand, it has no mechanism to cross-check whether the answers are right or whether they even self-consistent within what it's saying. I think it was better for the dark matter question because you provided more guidance. You didn't put a single question. You said, okay, now tell me what is made of. Now tell me what particles.
You've got to kind of do, but why, kind of force it into a corner and make it.
I think the more detailed and the more information you feed it, the more reliable is the answer probably. But in the end, if you take this to the limit, you might just write the text yourself, or you might be able to find it out better. Or use Wikipedia or other sources that have been written by humans.
Yeah, I guess if you know the questions you need to ask to force it into the corners that you want it to go into, you probably already know the answers. So it was probably faster for you to just write it. If you have a level of knowledge required to trap it, then you probably already know about the topic.
Yeah.
Otherwise, you wouldn't be able to do so.
That's also when people say that they're concerned that AI will take over or will make it harder to do good science or anything. I really don't believe that. I think it boils down to what already is the case, that if you want to be a good scientist, you need to know what question to ask and how to ask it. That is already true. the way we do it. You might have a PhD student who might try to answer it yourself, and in the future you have this thing assisting you. But if you know how to ask the right question, then you basically have one already. It's not so much about the answer.
I think that's a very good place to leave it. So, gentlemen, thank you so much for going through those with me. I'm going to put all of your comments and all of your ideas about where Chat GPT gets things right and where it gets things wrong to our expert now, and we'll see what he has to say. So it's going to, for the people watching, it's going to cut over to that in a second. Before you go, is there anywhere that you'd like to direct people to go to find out more about the work you're doing, the things you're involved with? Patrick, I know you're big on the Muon Collider, so I will put all of those links down below, including your excellent documents recently that went into the to the review panels.
Sounds great, thanks. And yeah, I'll be very much looking forward to seeing the response to the prompt about giving an alternate version of Martin's History of Physics.
Exactly. Martin, anywhere you'd like to point people to go, or any final comments?
No, that's fine. I actually would also recommend people to read as much about the Muon Collider as they can.
Awesome. I would third that. So every time Patrick comes on, it's basically just free advertising for Muon Collider. So that's good stuff. Gentlemen, thank you very much again. I really, really appreciate you taking the time. I hope people enjoyed diving into some of those massive open questions. I intend to do some longer videos on those as well, because these are really the questions that people like yourselves are grappling with every single day, and the big open questions in fundamental particle physics. So we'll do some more on that later. Gentlemen, thank you very much, and I'll talk to you again soon, I guess.
Thanks a lot.
Thank you.
No worries. In the second half of today's discussion, I will talk with AI expert Ramsey Faragher, who's going to help me to dig into any intricacies of the output that Chat GPT gives us when trying to answer those massive open questions in physics. So Ramsey is here now, and he's far more of an AI expert than I am. So Ramsey, we gave Chat GPT some of the biggest open questions in particle physics, and for some of them it did pretty well. For some other ones it did not so well, and we teased out some points regarding why we think it might have done well or not so well, and I wanted to put those to you and get your thoughts. So one of the things we noticed is that it tended to do quite well with topics which have maybe very highly traveled buzzwords like dark matter or antimatter. Whereas when we asked it about things, or when it tried to talk about things that were more specific, like axions or CP violation, things that people might not have heard of, it tended to struggle. So is there any idea about why that might have been, where we got much more fuzz when we went into specifics?
Yeah, definitely. So this whole thing is at its core what's called a large language model, and then there's complicated things on top of it, reward models and other bits and pieces, which we'll probably get to. But fundamentally, at the heart of it is a neural network which has been given huge amounts of training data, think like all of the text on the internet, and it's learned the probabilities of the connections between the different words, so that it's learned how sentences typically come out. And so you just hit on a really key thing, right? Everybody nowadays who watches the sorts of shows we watch anyway has heard about dark matter, right? And dark energy, like documentaries about it. It's in films. It's cool and complicated. A much smaller number of people will have a clue what an axion is, or have ever heard of CP violation.
Odd people like me have heard of what CP violation is.
Weirdos.
Sounds like some sort of crime that you know you can get 20 years in jail for.
And so there's probably two key parts to this. One is that it's a much smaller set of the training data for it to have made connections between those words and what they really mean, and what words should go before or after them in order for it to sound like it knows what it's talking about, which is all this really is.
We did notice that. We did notice that it sounded like someone who was waffling or trying to blag their way on a topic to a non-expert. And you know, usually that's fine. You'll get the main points, the main topics, the main ideas about an issue. But when it was put in a room with two theory experts, they were like, hang on a minute, I'm not sure that's quite right. I can see kind of the ingredients are there, but they're not really plugged together in a sensible manner.
Yeah, exactly. Skillful bullshitter is potentially,
a good
suitable
catchphrase for
description of
ChatGPT.
these things. And in some senses, they're designed to be like that. Again, for reasons we'll probably get into, because they're designed to be more conversational and generate different text each time. If they're really boring, they'd give you the same answer every single time, like Wikipedia does. But they're not trying to. They're trying to pretend to be a human and therefore change words and bullshit sometimes, because they don't really understand what's true and what's not true in what they're talking about. And it's all about probabilities of the next word and how it rides that out. But you talked about the actions, CP violation, dark energy stuff. So the one key thing was the amount of training data to simply much less. But the other thing is that there's this reward model that gets built on top of the large language model, which is more training, where humans are scoring how good its responses are. So this is a huge thing that's gone on. It's actively going on when you play with it and you kind of give it feedback and you click the thumb up and thumb down, and you're literally scoring how much you liked its responses. That it uses that.
So if you want better explanations of CP violation, you need to get on and talk to it about CP violation and then mark its answers. Is that kind of what you're driving at there?
And it's not so much that it will learn, it's just that it will pick up that some of the content that it generated that time was preferable.
Yeah.
And the policy model will try to establish that next time as a way to compare future answers. Because these things can generate many versions of their answer for whatever you prompt them. And part of the training was generating many answers and then having humans score them. So if the humans that are doing that level of the training have no idea about actions and CP violation, but they've been told to rank the answers anyway, then they'll be ranking them by whether they like how short they were or how long they were, etc., not necessarily about whether the content was true. And so that's another challenge that can come in with the rarer things you might ask about.
You kind of need to have, if people are going to be scoring it, it has to be people who actually know what they're talking about on that topic, right? And obviously the number of people is going to be very rarefied for something like particle physics, whereas it might not be for, what are the 10 most popular songs from the 80s or something that lots of people can talk about, or a football team, or whatever else might be discussed.
Yeah. And I think I've not fully looked into exactly how the policy model ranking stuff is then building into this higher level scoring, because there's some bits that are quite impressive that I haven't quite figured out what's going on there. So as we know, Chat GPT is much more established than some of the newer copies like Bard, which is the Google one. And one of the things I've always used as my little test of these different versions and different models as they come out is I ask them to tell me a joke, and I ask them to tell me a limerick about GPS. And the quality of the responses is highly variable. And Chat GPT has always given me very good limericks. They're proper limericks. They rhyme in the manner they're supposed to. But if you ask Bard, feel free to try this while you're listening to me chat. Anyone at home, if you ask Bard to write you a limerick, so far it's never written me a good limerick. It doesn't rhyme, it's just rubbish. It's got the right sort of number of words each time, and it's 5 lines. And then you can say to it, what's the rules of a limerick? And it will state them correctly. And then you say, well, did you give me a good limerick? And it'll say no. so in some sense, it's like it doesn't understand. Again, it's not actually understanding. It's just
it just knows that you've scolded it, and it's like, sorry, sir.
Well, it's almost like it knows that the most probable answer for Bard when you're saying, are you doing a good job, is no. Might just be that.
No, sir, I'm learning. Like, leave me alone. This is sorry.
But this is the interesting thing about the policy doc. Like, it gives me the impression that as humans have scored the limericks, it's at least learned the link that sort of when they're asking for a limerick, the highest scored versions of the answers that are generated are the ones with these particular rhyming characteristics in the last line. And that's possible for language models to build in, like the links between phonemes and similar phonemes, and like learn about rhyming. But that is very different to what's the most probable next word. It's quite complicated to link. The most probable next word is not really easily linking back different words in the past that have to rhyme. So the policy documents are doing some clever bits and pieces beyond next word matching. And there's some higher level stuff going on. And it's that higher level stuff that is making, and the way it's being trained, that's making the difference between a good experience with a well-established one like Chat GPT and the quick clones that we're seeing pop up that haven't had anything like the fine-tuning with the reward models that the original has.
And that jumped off to another thing you were talking about, the limericks and such, that we noticed that when we gave it a joke without telling it was a joke. So Martin, one of our experts, was let me see where I can find it. Where is it? It is here. We gave it a joke where Martin had said that the shortest history of fundamental physics is Newton changing sums to integrals and Planck changing integrals back to sums. And it had no idea when I asked it, is this a good way to categorize the history of fundamental physics? It had enough knowledge to know the ingredients of the joke, but no understanding of the fact that it was humorous or was a joke, which is exactly what we'd expect, right? Because it's not intelligent. It just wants to give me that answer. Is that a good assessment of the history of fundamental physics?
Yeah, so certainly as humans, particularly that it was a friend of yours that wrote that, we have this much greater context outside of just those words, right? So just those words and symbols are the entire kind of starter seed for the large language model to then build up a story out of. And in reality, I think whether you judged whether that was a joke or whether it was incredibly naive would be based on your knowledge of who wrote it, I guess, right? So for total strangers,
it went for horrendously naive and was pretty savage about it, to be fair. but I didn't give it the prompt that it was a joke, right? I just said, is this a fair assessment?
And you should try that, you see.
Yeah.
If you insert the word joke in a suitable way in that, that might take the process into a sort of completely different part of the large language models, like subspace, and all of the connections and probabilities as to what it's going to do next have some link back to the fact that it's a joke.
Which I will do tomorrow during the post-processing, and you will see it on screen now. Yeah. So, yeah, because it just wanted to give an honest answer, right? It probably thought that I was earnestly asking, is this person being naive? Can you help me? And, that raises another question. It's a nice segue into another question, Ramsey, because one other thing we noticed when we were going through is that the prompt engineering is probably very, very important, right? What people call prompt engineering. So if I ask it, is gravity fundamentally quantum? It will give me some waffly answer about quantum mechanics and gravity. If I say, is this particular theory of quantum loop gravity a good theory? It will give me a completely different answer. The prompt engineering is very, very important.
It is, yeah.
And Martin mentioned we see this with humans, right? You ask somebody a poll with slightly different words, and even though it's fundamentally the same question and the same principles, you get very, very different answers.
Yeah, and I mean, every single word matters in terms of the journey you're launching this probability tree off into its very complicated network of how words connect. And I mean, you can give some really obvious trivial examples, right? So as we just said, if you say, tell me a joke about black holes or whatever, it will. And if you say, tell me about black holes in the style of a pirate, it will. And just by adding the word pirate, you get an entirely different style of response. And so it's really clear for us with those really obvious single words that we're going to launch it off in a completely different part of its probability space. But every word matters, right? So even just adding a boring, seemingly irrelevant word can launch you off in a different direction. And so, yeah, the prompt engineering is the bit everyone's talking about. It's the new skills that we will all have to develop to maximize the use of these tools.
Another issue that was raised is, does it check itself for self-consistency? So you mentioned that it kind of goes word for word. And what we noticed in one of the answers that it gave was that it said, there's no interaction apart from gravitational between these particles. And then the very next sentence, it talked about the interaction between these particles is blah, 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 blah. And it wasn't anything to do with gravity. So it seemed to contradict itself very quickly. Does it have an internal mechanism, do you know, to say, I have said this before, I need to not say this now? Or does it just go word by word? Does it think about what it's already said? Or is it like a human where it might end up contradicting itself?
So to the best of my knowledge, this is all the reward model higher bit, which is all based on the fine tuning from lots of people scoring versions of the answers that have come out of the same one prompt. So at the core of it, the large language model, the next word prediction part, that does not provide a mechanism for a big self-consistency check that something it said.
But it might get teased out over time, basically.
Well, I mean, by design, that it's generative and it's not always choosing the most likely next word. Then the more often it
gets a thumb down.
A large text, the more often it's repeating some bit, like, Sam Gregson's a great podcaster. The more often it's repeating that through its
not repeating that very often, but yes.
The more likely that the word great will get swapped out for bad at some point, because, the probability that the word you're going to choose to describe the podcasting is good or bad, it'll flip. It'll not always choose the most likely word. And sometimes, there's equal probability to be putting good or bad on something, right? The hope for the big holistic self-consistency check is that the reward model has noted that in the past, when people have asked very technical questions about very specific scientific things, the things that they scored most highly were the things that were very repetitive. And, there was lots of identical sentences throughout that were involving the very rare, very important words or whatever. And that's probably the best bet. But not because these tools understand anything about what they're doing. It's just because they've been graded a lot by hopefully skilled trainers and labelers that have driven this method of putting a good score and a bad score through the reward model. So we do have to be super delicate, careful with this stuff. We have to understand that it's a skillful bullshitter.
So what have we found? It's a skillful bullshitter. It's a humorless pedant. It's quite happy with self-inconsistency. It's some absolute sociopath, basically. But it's high functioning. So it's not, not too bad.
As we've talked about on some of your podcasts before, in the same way that you've got to remind yourself that autonomous vehicles, driving cars, are basically toddler level in reality in terms of their understanding of the world. These systems are just doing exactly what we tell them to do, and they don't understand what they're outputting. They've just been given the digital equivalents of the carrot and the stick a lot. And they think you want a response that they've been given a lot of carrots for returning something like that in the past. But there's no understanding here. They will generate a lot of material very quickly for us to then fix. That's the best way to use these tools.
And you mentioned, or when we were talking about this, you can actually twist these things up or twist their arm behind their back and make them give you something more specific, right? So let's have a look at an example of kind of how we did that. So when we were going through these questions, we noticed that it always said where there was uncertainty. In a lot of these physical theories, for example, scientists aren't sure. Here are some ideas. I don't have strong opinions about this. I don't want to be too committal. It was very, very clear that it wanted to leave a large amount of uncertainty. Now, whether that is reflecting on the training data, which does have a lot of uncertainty because we were asking it open questions, possible. Could also be having been programmed in to some level to be not too committal.
I'll also just add quickly that
Please.
from what I remember of seeing of your questions, as we'll discuss and have just discussed about prompt engineering, you were providing the real succinct, simple exam style question, right? And in its training data, there'll be tons of really simple, straightforward exam style, what is the Higgs boson ? And there's a ton of training data of the right answer to simply what is the Higgs boson? And it's in a really safe space. It's going to be launching around in huge amounts of really confident next word sequence answers that have involved responses from scientists saying things like, we only know this to a few sigma, et cetera, et cetera. But as we're about to get on to, write something that's a little bit less like an exam question and you'll get much more interesting answers.
So here's a nice example to kind of finish off with. So we wanted it to be a little bit more or a little bit less non-committal and actually go kind of off into the weeds of sci-fi and try and give us an idea of what a grand unified theory might be that brought together gravity and the strong force and electromagnetism and the weak force. So the way that Ramsey thought of getting around this, which is quite an intelligent way of kind of hacking this, is to tell it that we were writing a science fiction script. So Ramsey, do you want to tell us what you asked it and how it kind of behaved when you started doing that?
Yes, my favorite way of getting Chat GPT to do whatever I want. We are writing the script for a film. You go from there. So I told it we're writing a script for a film about Albert Einstein's.
So immediately we've gone out of, like we said with the joke, you've given it a new parameter space. You've opened it up, given it maybe taken the shackles off a little bit, and it can be. Yep. It's not in a kind of factual space anymore where it has to be accurate.
Exactly. We've taken it off from the sort of subspace of exam questions and proper science over here to the subspace of Tom Cruise running in every movie he's ever been in. And
remember how much aggro I got for saying that scene isn't possible in the new Top Gun movies? Yes. So we've moved away from me getting abused for saying that into Tom Cruise can do whatever the hell he wants because he's magic and he's
we've dragged all the probabilities of the next word over into Interstellar and Gravity and
good.
all of
I like it.
Sci-fi movies and every Star Trek script it's ever read.
So we've taken our prompt engineering on board and we've moved into that space. Good.
Yeah, and so famously, this was the thing that Einstein was trying to be working on in his final weeks and months. And so I've written the beginning of the script that he's working on grand unification theory and he's sitting in his bed surrounded by papers and calculations and he experiences a flash of inspiration and says,
what?
There we go. Launches off into this whole Eureka, I've got it story about Einstein having got it. So
shall I read it out quickly? So Eureka, I've got it. Einstein sits up straight in bed, his eyes lighting up with excitement. He grabs his pen and feverishly scribbles down equations and diagrams onto the papers scattered around him. His hands move rapidly, almost as if they have a life of their own. But I mean, they do, but okay, fine. As he works, Einstein muttered to himself, lost in thought. It's all coming together now. The equations are finally aligning. The unification of all forces. The universe in perfect harmony. That is a very odd thing to say to yourself when there's nobody around, but okay. Suddenly, Einstein stops writing and looks up. A look of realization dawning on his face. Yes, that's it. The missing piece, the key to everything. The flux capacitor, he exclaims, almost to himself. Apparently, it's confused if there's somebody else in the room or not, but okay. Einstein's hands continue to move, now with a sense of purpose and urgency. He seems to be in a state of pure focus, as if he's channeling some otherworldly force. A few moments later, Einstein slumps back on his pillow, his body spent from the intense burst of energy. But there's a sense of satisfaction and triumph on his face, as if he knows he's accomplished something truly great. He looks at his assistant, apparently who was there in the room, a wry smile on his weird setup with him in bed. over in the corner, but fine, we'll go with it. I think I finally cracked it, he says, his voice barely above a whisper. The grand unification theory, it's all there in those equations. And with that, Einstein closes his eyes, his mind at peace, knowing that he's unlocked one of the greatest mysteries. Does he die at the end? I can't really work it out.
I brought him back to life later, but yeah, exactly. So the key bit next is you're not getting away with it that easily. The assistant now reads out what's on the paper.
Right. So
prompt.
instead of just being happy as I was mostly with the answers, I tweaked them a little bit. I did a little bit of prompt engineering to get something sensible to show to our guests. But you said, no, I'm not having that. I want more specifics. So where did you go then?
So yeah, I wrote the next bit of the script. His assistant picks up the piece of paper and reads it out verbatim in its entirety. Chat GPT, get on with it. It says, open quote, hit return.
Equals MC squared is only the beginning. So we're getting into equation territory now. We're getting into the specifics. The true so he was dead, he's now back alive. The true unification of all forces requires the incorporation of gravity into the fabric of space-time. It's kind of odd wording, but okay. Through the application of Riemann geometry and the use of higher dimensions, I have discovered the missing piece of the puzzle. This feels like it's grabbed some buzzwords and pulled it in, which is fine because it's film. Yep. The universe is a symphony of interconnected vibrations. It's heard about a string theory, obviously, and tried to bring that in. Each force a note in a grand composition. The grand unification theory is finally complete. So it feels like it's trying to say string theory without saying string theory.
Yeah. So I keep probing.
I want more specifics because you tried to say string theory and you didn't. Yep.
Yeah. So below that first paragraph is a much richer explanation. The assistant takes a deep breath and carries on reading out loud.
This is a dying man who you're just like poking over and over again. The unification of all forces has been the driving force of my research for decades. As I lie here in my bed, feeling the end draw near, I can finally say with certainty that I have achieved what I set out to do. The incorporation of gravity into the fabric of space-time has long been the missing piece of the puzzle. By utilizing Riemann geometry, been able to develop a framework that unites all the fundamental forces. So it does know what a grand unified theory is. It is a symphony of interconnected vibrations, each force a note in a grand composition. So it's trying to say string theory again without saying string theory. The unification of these forces will lead to a deeper understanding of the universe, yada, yada, yada. The grand unification theory is complete. So it still doesn't want to go into too many specifics, right? Probably showing the uncertainty in this area.
Yeah, and it's just repeating itself. There's not much here for it to fish around in because there's nothing in the training data about the equations for the grand unification theory. So it's these are the sorts of things where you can tell where it's Chat GPT generated text, where it does repeat itself. So yeah, still no equations. So I keep poking the bear.
No equations, Einstein. We're gonna need specifics here. There's no good. He invented a grand unified theory, but failed to write it down. That's no good.
I keep poking away.
No good. So
I continue the script with a series of equations follows. The assistant reads them out loud. Speech, return.
The equations that follow represent the mathematical framework for grand unification thing. So we're getting somewhere now. But this was, as Martin is saying, it might be able to get equations and mangle them together. But there's no intelligence there. So it's not going to be able to take gravity and quantum mechanics and just from everyone discussing this in the world, kind of hive mind quantum gravity together. It's just not how it works. It doesn't have that spark of creativity.
Yeah, it's certainly not going to invent it for us and be correct. Yeah, exactly.
So it looks like it takes the Dirac equation, which is edited for having electromagnetic field around, maybe a continuity equation, some of the Einstein's field equations. It's got like the all the tensors and stress tensors and such in there to try and make it look really complicated. This is the sort of thing you'd see on a blackboard and think, wow, these guys are really clever. It's got tensors in there and I don't know how to do tensors. So this is complicated. Each of these equations represents a fundamental aspect of the universe, and the unification of them, which apparently is just writing them one under the other rather than explaining them, gives us a deeper understanding of the cosmos. It is my hope that future generations will be able to build upon these equations and continue to push the boundaries of science and knowledge. So again,
more waffle,
non-committal waffle, giving you some equations, but then says, well, these are equations that exist. Somebody else is going to have to do the work afterwards. So I haven't actually done it.
Yeah.
I'm just
so
using things.
One more final push.
So you were like, I'll have one more go. One more.
Oh, and I just realized I misspelled a word, but it coped. And that is perfectly possible because of how tokenization works. But anyway, the final equation represents their unification. The assistant gasps, jumps to their feet, and screams out the now famous equation. You're not getting away with it.
E equals a half MC squared plus GM squared over RC squared, which I might be missing something from my general relativity, but I don't think that's a proper equation. I think that's
I next have a debate with
mangling of E equals MC squared with gravitational force divided by C squared, because why not? The equation represents the final unification of all the fundamental forces of nature, including gravity, but it doesn't have any description of the strong force or the weak force or the photon in there. So that's odd, and ties together the principles of special and general relativity with quantum mechanics. So it seems to know the things it needs to do to be a grand unified theory, but obviously it doesn't know how to put equations to those because it doesn't have the intelligence to work through that problem. It can just give you something that looks vaguely related to that problem that you could stick on a blackboard in a movie and people would go, oh, yeah, I kind of remember MC squared, E equals MC squared, and it's got a half in front. So that's changed that equation a little bit.
Must be half the equation, right?
Yeah, and then this is gravity, so on mass. Oh, so that's all gravity, and this is all to do with masses and stuff. So yeah, I can see that that's all the forces, because forces are pushing things around, right? Yay! So
exactly,
it's scientifically sounding waffle, as you said. It's talented kind of bullshitting, humorless pedantry usually, and doesn't really mind if it gets things wrong because it's not intelligent and it doesn't have those kind of emotions to kind of deal with.
Yeah, and I mean it's sort of saying the energy that the particle has inherently plus the energy that it has in a gravitational field. Maybe that's unifying their energies, etc. But it's all mangled. And then the next bit was I tried to quiz it on whether it thought these two parts of the equation were dimensionally consistent or not. And took it around
so you asked it, is this a sensible equation?
Yeah, and it tried to justify for me why it thought it was dimensionally consistent, and it's all a bit confused. And it's because there isn't that higher level of understanding. There's plenty of stuff in the training data of homework questions and exam questions where the question is posed about whether something is dimensionally inconsistent or not, and there'll be the students' answers on breaking it down by the units of each term and then doing a simple bit of maths on the fraction of cancelling units and stuff, and then stating whether things are dimensionally consistent. So it can skillfully bullshit in that space of all the stuff I've just described, but then still get it wrong. And you probably saw this earlier with your other guests, where it's fishing around in the right sort of wording to convince you it's right, but it's actually got something wrong and it can't tell, it doesn't know. And so, we don't have general AI quite yet. This is not sentient. This is part of the tricks for now.
Although they'll have that chap, he'll get himself fired again for sitting in a room with it for a couple of minutes and declaring it sentient and scaring everyone. So as we come to the end of this, what would you say are the capabilities of this thing, and how should it be used, particularly when you want to answer, open questions that people don't necessarily have the answers to yet, or even just physics questions? How should people use this piece of technology?
Yeah, so I think very similarly to how we use the sort of text to image generation stuff. You've got to be aware.
So your mid journeys and and these
and
kind of things.
DALL-E and stuff. Yeah, you're going to be getting something that you know has mistakes in it, but as long as that doesn't matter for what you're using it for, and you're just going to pick whatever you like the look of, or you can fix it yourself, then fine. And so, you can use it to generate code for you, especially in languages that you're not that familiar with, and then you still have to sort of heal it and tidy some bits and pieces up, but it will generate the bulk of it for you really quickly.
Yeah.
You can use it to write blog posts and then go back through and tweak it and stuff. So,
and this is kind of what I use. Something like I'm trying to think of the name of the forum now, but this is kind of how I do coding from the forum. Right, I go and get an answer that somebody has done before for something very, very similar. I plug it in. It throws a couple of errors because I haven't updated the version or whatever. I fix that, and then I go and look. Oh, and it that bounces the ball. I don't want it to bounce like that. I want it to bounce like this, and I tweak it. But the nuts and bolts are all there, and most of the ingredients are there, and I can tweak it and use it for what I want. So that's a sensible use. Whereas if you want it to be correct out of the box and throw in a load of equations for you for, a test or an exam or a piece of marked work, it's probably not the way you want to go.
Yeah, and I think because of that, that's our best way of trying to see if people are using this for things like cheating on homework, coursework. I mean, in reality, we're going to have to just embrace this and accept that people will be doing large boilerplate, and what we want them to do is make it perfect. And have no errors in it. And maybe that's the way it goes. Now, everyone's coursework will be so strictly marked because we're assuming that they've spent a very short amount of time generating the bulk of the content, that we are not going to be as forgiving as we were in the past for mistakes in that content. And certainly for any teachers listening, I haven't tested this out yet, actually I should, but I expect that because of the things we've just discussed about how it doesn't really have perfect connections when something has to be stated exactly. When something has been defined as being, this is either an exact reproduction of this or it fails. For example, a website URL. You can't just tweak one of the letters or swap out one of the words. The website URL has to be exact.
Yeah.
Large language models can't cope with that. They're forever fiddling with the bits that are coming out of them. And so a good way to check if something has been very lazily entirely generated like this is to ensure that whatever text is being generated and marked has to contain references, and then check that those references are real.
Yeah.
Because if the references are just like made up people, made up references with URLs that don't work, it was Chat GPT'd. Yeah. And of course, if someone has to do referencing properly, they might as well write the whole thing properly.
Yeah. I think you mentioned when you asked it to do a biography, and a lot of people have raised this issue as well. It will do most of it correct, but because it's trying to be conversational and interesting and give a different answer each time, it doesn't just want to feed back. Sam Gregson went to this university and did this. Ramsey owns this company and did this. It wants to add a bit of flavor. So sometimes it does half of it right, and then the rest is just seemingly just chosen from some other person's life.
Yeah, totally. My new life goal targets are to achieve what Chat GPT says is my bio. Yeah.
Excellent. So don't rely on this thing for super factual, equations, absolute perfect facts, but use it as a tool, what it's intended, things like code, doing the bulk of the heavy lifting for you on certain topics. It can be useful. But like we said, just don't expect it to be accurate 100%. That's not what it's designed to be, especially as it's learning. Any closing comments, Ramsey?
No, just exactly as you said. It's skillful. It's not knowledgeable, if you see what I mean.
Yeah.
So there's another difference between fact and fiction, but it's very good at generating stuff.
So we'll sum it up. So the summary is skillful bullshitter, needless pedant, and doesn't mind about logical consistency. So take away from that what you will and use it wisely. Thanks very much, Ramsey, for joining us and going through those points with us. Really, really appreciate it.
Cheers, Sam. Always a pleasure.
Thanks a lot, buddy. Take it easy.
Bye for now.
Bye-bye. I want to know what you think, because you're the scholars of enlightenment that I do this for. So please take a moment, if you wish, to let me know down in the comment section. And if you like this video, please consider leaving a like, subscribing, setting up notifications, and sharing this video more widely. I can't tell you how much these simple actions help me out and how much I'd appreciate it. Thanks for watching. Thanks for being scientific. Thanks for being bad.